Hey folks, time for the next lesson. Looking at the Earth, Sun, and the Moon. So these are kind of the three things that the motion of really affects a lot of things on Earth that we may not realize. We're going to look a lot more detail into the suns and how suns work later in the course in Unit 3. But for right now, we just want to look at how does the sun influence the Earth. So start with the Earth. The Earth is the home for every human being who has ever lived. In fact, there are only 13 people who have ever stood on anything other than the Earth in basically everywhere. It's a small rocky planet surrounded by a thin oxygen atmosphere. In fact, the atmosphere is a lot thinner than you think. So if you were to take an average sized globe and put a sheet of paper on top of it, that sheet of paper is actually 90% of the atmosphere. So it's a very, very thin atmosphere. We think it goes way out, but it actually really doesn't. It's located 150 million kilometers from the sun. And because these numbers get really, really huge, that's again, put 6 zeros after 150, we use different scales in space. So we use light years. We also use something called an astronomical unit. And an astronomical unit is basically 150 million kilometers. So we compare how far things are within solar systems to how far the Earth is. So if something's 2 astronomical units away from its sun, it's twice as far as Earth is. If it's 0.5, it's half as close as Earth is. So this is what we call the perfect distance because it's not too hot or not too cold for our sun. Because of that, we actually call it the Goldilocks zone. What do we mean by not too hot or not too cold? Well, the biggest condition for life is water, liquid water. So you're basically at a distance where the sun gives you enough heat that there's liquid water for at least part of the year on that planet. That's what we think you need to actually have life happen. We think there needs to be liquid water. And that's the first thing we look for in planets. So we call that the Goldilocks zone. Downside, it's not always going to be the Goldilocks zone. As the sun grows, it gets warmer, and in about 150 million years, Earth is actually going to be out of the Goldilocks zone, which is why it might make sense for us to be somewhere else, before the oceans get too hot and boil off. So, the sun produces all the energy from our solar system using something called nuclear fusion. Again, we're going to look at that in more detail later in the course. It contains 99.86% of all the mass in the solar system. That's a crazy number. That literally means that 99.86% of everything in the solar system is the sun. All the planets are literally, 0.14% of the mass. It produces 384.6 yodawatts. Yes, yoda is a number, not Yoda, but Yoda. So that's 10 to the 26 watts of energy. So that means it's producing something with 26 zeros, joules of energy per second constantly. And it's 695,700 kilometers in radius. So if you want to take perspective, this is actual size. So if this is the sun, that's Jupiter. Earth is right there. That's Earth. You could literally put 1,000 Earths end to end across the width of the sun. Or to give you another idea, if the Earth was there, the moon would be about there. So, Earth's moon is 384,000 kilometers from Earth. It's 1,737 kilometers in radius. It's about 1/6 the size of Earth. That's why you have 1/6 your gravity when you're on the moon. It's rocky and it has no atmosphere. So one of the neat things about the moon is the astronauts' footprints are still there because there's no air to actually, or no wind to blow it around. So the astronauts' footprints when they walked on the moon are still there, which is kind of cool. So this is an actual, again, this is comparative size of Earth. Of course, it's not that close. It's actually well off the screen. So, there are two terms you need to understand when we talk about motion in space. One is rotation, one is revolution. And you might even hear me make a mistake and use the wrong word, but it's worth sort of thinking about to make sure you don't. Rotation is when something sort of spins along its axis. So if you've got something and it's rotating like this is rotation. So it's spinning along an axis, And the Earth rotates one day every 24 hours. That's why we get day-night cycles, is that we're basically facing the sun at one point. In 12 hours, we rotate, and we're now on the back, so we get nighttime, and then we rotate again, which gives us day. Now, that's actually really important. If the Earth didn't have that, and by the way, eventually it won't. We're slowing down. Don't worry, way off in the future. One side would get way too hot, one side would be way too cold. And we'd call that tidally locked. And basically the planet would become unlivable, except maybe a tiny little part right at the edge of where the day-night is. Of course, there could also be problems with winds and weather. Revolution, so rotation is going around in a circle. Revolution is when one orbit, it travels in a circular path around another, so due to gravity. So the Earth revolves around the Sun one every 365.25 days. It's actually not, they don't sync up the days and the years. That's why we add an extra day every 4 years, is that the Earth goes around the Sun in 0.25 of a day. So every 4 years we need to add an extra day, otherwise it'll fall out of orbit. Well, it won't fall out of orbit, it'll fall out of, sequence. The Moon revolves around the Earth once every 27 days. So that's why we get the different cycles of the Moon. Now, seasons are an interesting thing. Now, you ask most people, they'll tell you, well, it's summer when we're closer to the sun and winter when we're farthest away. But that doesn't really make sense because it's summer in Australia when it's winter here. So Australia can't be closer to the sun than Canada is. That doesn't really make sense. What it actually is that the Earth's axis is tilted at about 23 degrees. So when it's the summer, we are tilted so that we are facing the sun and we get more direct sunlight. So you get more sunlight per area, which gives you more energy. In the winter, we're facing away, so we get less sunlight and less direct sunlight, less amount of the total sunlight, that less energy, that's why it's colder. Whereas the southern hemisphere, when we have winter, gets a lot more of the sunlight, and that makes it summer. And it's exactly the opposite when we go around. We now get more of the sunlight in the summer, and the southern hemisphere gets less. So that's why we have a seasons, a day and night. If the Earth, sorry, day, night, summer, winter. If the Earth was totally straight, there wouldn't be any seasons. It would always be the same. Now, another cool thing that the orbit causes is the orbit of the Moon around the Earth. Everything with gravity pulls on everything else. So the Earth pulls on the Moon, but the Moon also pulls on the Earth. And the reason the Earth doesn't rotate is it's way bigger than the Moon is. But water on the Earth actually does get pulled towards the Moon. And we can see the effect in water. So as the Moon goes around, the water on Earth follows the Moon and bulges where the Moon is. That's what actually creates the tides. And that can be up to 8 meters in some area, where the tides can be 8 meters higher or 8 meters lower. Because as the Moon goes around, it pulls. Similarly, you can actually see a wobble in the Sun because of the Earth going around it. And that's actually one of the ways we look for planets, is we look for basically the wobbles in the Sun. All right, phases of the Moon. Now, one of the biggest misconceptions people have is that they think the full moon is when the Moon's in front of the Earth. Well, that's actually not the way it works, because the Moon doesn't give off its own light. It reflects sunlight. So it's when the Moon is on the far side of Earth that we actually see a full moon, because all the sun's rays hit the Moon, reflect back to Earth. When the Moon is beside Earth, we only see half of it lit, because this half doesn't get any sunlight. When it's in front of us, we actually get a new moon, because all the light reflecting off the Moon is going in the other direction. By the way, I do not expect you to memorize the different phases of the Moon. You should know new moon, full moon. but that's about it. And it basically starts with a crescent on this one on the right side, ends up with a crescent on the left side. By the way, this is always why you're going to see we only ever get eclipses when there are full moons. So, what an eclipse is, the reason we do see it, you may think, well, wait a minute, how do we see the moon at all when it's behind the Earth? Well, it's because the moon's orbit is tilted. So most of the time, when the moon's behind the Earth, we can actually still see it. It's not being blocked. Sometimes the moon does get blocked by the Earth because when we're going around wherever you are, you're actually seeing it, and that's what's called a lunar eclipse. So when the Earth-Moon moves into the shadow of the Earth, we get a lunar eclipse. Solar eclipses actually happen as much as lunar eclipses, but because the moon is so much smaller, they only happen to a tiny, tiny part of the Earth, and it's usually over the oceans. So it's very rare, like for example last summer, that we actually get a solar eclipse where the shadow of the moon actually passes a certain area. Most of the time, we don't even notice it because it's somewhere in the ocean. The shadow's going through the ocean, so you don't notice it. All right, so that is the, oopsies, meant to move that. That is the effects of the sun, the moon on Earth. So the main things is, I want you to remember, is rotation, is spinning, revolution, moving around something. Seasons are because day and night is because of the rotation. Seasons are because of the revolution and the fact that the Earth is tilted. Tides is due to the revolution of the sun, or sorry, of the moon, which also creates the phases of the moon and creates solar and lunar eclipses. All right, see you next time.